Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I'm a theoretical physicist and I specialize in cosmology. So I study the universe, the contents of the universe, what is going on in the universe, what's happening, the history, the content, the evolution of the universe. It's a great topic. I love talking about cosmology. And I love chatting to people about all of the cool things I get paid to work on and stuff that I like that it's not necessarily my job. I just like chatting in general. I'm apparently a very chatty person. So to anybody who's new, first-time viewers, welcome to Cup of Cosmology. To return viewers, excellent to see you back as always. I already see Scott, Ange, David in the comments. Great to see everyone. Thank you for joining always. Seems like you people are here every week, and it's so nice to see that you still come in every week to hear me ramble about random stuff in the universe. So if you are new here, please do subscribe to the channel if you like what you hear. Leave a comment below, like the video. It really does help boost the videos and help me reach a bigger audience. So please do all of the usual YouTube engagement things to boost the viewership. If you're watching over on Twitter, it's great to see that Twitter is still somewhat alive. But feel free to head over to YouTube if you want to join in the conversation, because that's where you can actually interact with the comments a bit better. Hey, James in Thailand. Wow, I'm surprised that you're still tuning in over from Thailand, but it's great to have you here as always. It's great to see all of the regulars. Hey, James. Yes, great to see everyone here in the comments, and nice to see you all chatting amongst yourselves as well. I like that we have a little community going here. So yeah, I'm a theoretical physicist. I specialize in cosmology, so that means that I study a lot of cool stuff happening inside the universe. And the point of this show is that you can ask me anything you want about cosmology, about space, about science, about physics, about what I work on, about academia, basically anything you want. You can throw any questions at me, and I probably won't have all of the answers. I definitely won't have all of the answers, but I will do my best to try to answer as many questions as I can. Might be leaving in a bit. Well, it's nice of you to drop by, Scott. It'd be nice to have you here while you can stay. So I don't have a topic planned today. This means that it's up to you to ask questions and guide the conversation in any random direction. See what you usually when I do this, people hit me with really tough questions, so it's always fun to do. So as always, you can ask me anything just to set the scene a bit. Throughout most of my masters and my PhD, and yes, earlier on in my first postdoc, I worked mainly on dark matter. So what is dark matter? Well, we know that the universe has three main components. Everything you see, everything you're accustomed to, everything you interact with on your day-to-day basis, everything from the stars in the night sky to me, to my team up, all of this is normal matter. Normal matter only accounts for about 5% of the energy budget of the observable universe. Then there's another big chunk, almost 26, just over 26% in the form of dark matter. Dark matter is this weird type of matter that interacts via the gravitational force but doesn't interact via the electromagnetic force. This means that it's essentially invisible and therefore very, very difficult to detect. Then we have the remaining 69%, which is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. And we don't know much about dark energy other than it's probably not black holes. Throughout a lot of the time in the past, I've worked on dark matter. So what I've basically been doing in a lot of my papers is asking the question of what can we do with dark matter and still be compatible with the universe. To answer this question, we use things like the CMB, less than 5 minutes today. Who had that on their bingo card? Less than 5 minutes. So CMB, cosmic microwave background radiation, oldest light in the universe, background light in any direction you look in the night sky. And this is a snapshot of what the universe looked like 380,000 years after the end of inflation. By looking at the CMB, we can learn a lot about dark matter, about dark energy, about normal matter. It really is a snapshot of the baby universe. So a lot of what I've been doing in the past is using this amazing map here to constrain the 26% of dark matter in the universe that we have here. People saying I should just open with that image. Well, I do. It's in my logo specifically so that it's the first thing you see. The CMB is always, always, always there. And I finally finished decorating my office. I've been here 18 months. It was about time. And I now actually have 3 CMBs up in my office. I have a big poster of the CMB, but it's an old version. I have a very cool holographic postcard that, depending how you look at it, it's the different CMB images from different satellites. And I have a CMB in the trans flag colors, which is just super pretty. So there are now 3 CMBs up in my office around me. But what I'm working on these days is gravitational waves. Now, gravitational waves are a really, really, really amazing topic. Gravitational waves are ripples in the fabric of space-time. They're tiny, tiny, tiny fluctuations of space and time. If a gravitational wave goes through you, you get longer, you get taller and thinner, and then shorter and fatter, but by a billionth the width of a human hair, so a ridiculously small difference. Gravitational waves are caused by dramatic events like black holes smashing together at high speeds of smashing together, producing gravitational waves, or by things in the early universe, like the universe itself, as it expanded, as it changed its makeup in the early universe, it could have produced gravitational waves. So what I'm working on these days is trying to understand if we'll ever be able to measure these gravitational waves from early universe signals. And I'm just throwing out a lot of things here to give you ideas as to what type of questions you can ask me. Of course, we can also go completely off tangents, off topic, and you can ask me why people were excited about Venus this week. What's up with that? As always, any and all questions are completely welcome, so feel free to ask away. And I do see there were some questions already. Question of when is the dynamic duo coming back? So a couple of weeks ago, two weeks ago, I had 2 people from my office join me, Ali and Lorenzo, and we talked about quarks and creativity in general relativity. And it was a super fun stream. I think everyone enjoyed it. We all enjoyed it a lot. We all promised at the time that there would be part 2. We're not yet sure when part 2 is happening, but it will definitely happen. So I promise those guys will be back at some point, but we don't yet know when. So I will have another stream with the dynamic duo, because those 2 are really fun to have on the show. So that's absolutely going to happen, but I don't yet know when. So maybe in a couple of weeks. Can't make any promises without talking to them, but I think I can probably get them to join at some point soon. Okay, it is the image that you look out for. Yeah, I know my logo is technically not enough. You will want to see the actual CMB image, which is why it's always ready and loaded right here on my slide deck so that I can flash it at any point. CMB that must always, always, always be shown. That is true. Okay, I said the universe changed its makeup. Yeah, we can pretend we're cosmetologists and study the makeup. I actually meant to say the markup of the universe and said makeup instead. Close enough, same difference. So, okay, so I don't need to talk about the volcano on Venus today. So I just dropped out like, why were people excited about Venus? So let me answer that question. People have found, scientists baffled, not baffled, scientists have found a volcano on Venus, which is pretty cool because it tells us a lot about the structure of the planet and the plasma. And it's a planet that doesn't have tectonic plates, which is an essential ingredient to having volcanoes here on Earth. But I'm not going to talk about Venus volcano because David Dunn is going to do that on his show later on today, which should be on Twitch, I believe. So do follow David Dunn on Twitch, on YouTube, on whichever channels it is to learn about the volcano on Venus. And that is good because I have not prepared volcano on Venus. So go and watch David to learn about volcanoes on Venus. And there was a question by James about black holes. I haven't read the question yet, just question about black holes. When I see a black hole represented, it looks like a tornado. It looks like a tornado shape. This is a black hole, deep and narrow, or shallow and wide, and do we know? This is an excellent question. It's a very, very interesting question. So black holes should be spherical. They should be spheres, or at least let's assume that we don't have a rotating black hole, just a standard short black hole. So a black hole that is not rotating. This should be spherical because you have an equal gravitational force in each direction. So most objects in the universe tend to be spherical unless there's something that's perturbed them. So black holes are actually round objects, but they're like little balls or big balls. Now the problem is how do you visualize this and what is actually happening around a black hole? Now what you often get, especially with more massive black holes, is an accretion disk. So a lot of matter that is gradually falling into the black hole. And this usually does end up in a disk. So what you end up with is something like this, like a nice little round thing with an accretion disk. And then depending where you're looking at it from, you have this accretion disk around it. Then there's also the thing that light is deflected around black holes because black holes are going to curve space-time dramatically. So light traveling around them is going to be deflected. So There is this famous image. I'm not actually sure if I have it in my slide deck. I think I don't. I'm just going to see if I have it there. There's a now famous image of the black hole at the center of the Milky Way and the black hole in the center of M87, where you can see this nice kind of orange donut around a black hole. Now, what you're looking at there is the light that's coming from all directions around the black hole is getting diverted lens. That's the word. It's getting lens and changing its path. So that nice round disk that you see around the Okay, I'm back in focus. My camera just did something weird. That glowing disk that you see is the light that is traveling around the black hole that is being deflected by the big, massive object that is the black hole. Yes, space donuts. I am looking for it, but I don't think I have M87 or even our black hole in my slide deck. The weird thing about Restream is I can upload PDF, so I can use like a slide deck, but I can't upload individual images. So any images I want to show you has to be preloaded in my slide deck, which takes about 10 minutes to upload and is done in advance before the show begins. So no, I do not actually, I just went through all of my images, can confirm that I do not have M87 loaded. So not showing that one today. But if you think about the nice orange glow you've seen in these images of black holes, that is just the light being deflected. Problem is depicting black holes because we always try to depict them in ways that is easier to understand, and often you'll see us draw pictures of black holes. And the most common one is if you have space-time in a grid, you kind of draw the wormhole-like thing with all the space-time lines converging down. So you often end up drawing something like this is space-time, this is a black hole that is curving space-time. So this is why you might get the tornado kind of idea. But technically, black holes should be spherical. Then it gets a bit more complicated if you consider rotating black hole, because there you can actually have kind of a ring-shaped event horizon around the black hole due to the way it's rotating. And this is like a ring singularity that we say. So to answer your question, the question was what's the kind of the shape of a black hole? A black hole is usually a round object. If it's rotating, you might have a ring-like event horizon around it, but it should be spherical. Problem is when we depict it, we have to put more dimensions than we have onto a piece of paper. So you put like 4 dimensions onto a 3-dimensional piece of paper, or a 2-dimensional piece of paper even. So then we just kind of draw it as disrupting space-time. But black holes are spherical objects. The ring of light you see around it is the light being deflected around these supermassive, around the black holes. And most black holes have this nice round shape, and then there is the accretion disk around it as well. So those are the that's the general idea. And I have my trusty plushy black hole here, and you might have noticed, and I've shown it before, it's a black hole, white hole, both 2 in 1, and I love this plushie. Also, it's a mood plushie. It's like I'm in a bad mood, I'm in a good mood. So you could use this. I'm thinking of getting one for the office, and then people can tell if I'm in an approachable mood or not. But I am always approachable anyway. Just sometimes. Yeah, anyway, let's not go there. As it accretes matter, will it get deeper or just fatter? Does that even make sense? It does make sense. What's going to happen is it actually grows. So the size of a black hole is directly proportional to the mass it contains. This is not usually the case because usually, as something grows, as you add more mass, the volume scales differently depending on the density. But in the case of black holes, the bigger the mass, the bigger the radius. There is a direct relation between them both. This means that as more and more matter falls into the black hole itself grows. So if you imagine you have this ball, matter falls into it, it's going to get bigger and bigger and bigger and bigger and bigger. So it gets fatter in a sense as it gets bigger in this kind of a growing sphere. The more matter that falls into it, the bigger it gets. Then, of course, you have the other side of it, where black holes can actually evaporate or emit particles via Hawking evaporation. And this is a weird phenomenon where you create 2 particles on the event horizon of a black hole. One falls in, one goes out. And at this point, you kind of need to return the energy that you've borrowed for creating these 2 particles. You borrow energy from the universe, you create particle and antiparticle. Usually these immediately annihilate and return the energy to the universe. However, if you do this at the event horizon of a black hole, one can fall in, one can go out. And at this point, you've borrowed energy from the universe, and the only way you can repay it is by the black hole losing mass. So even though it is not a particle that is being emitted from a black hole, and we have to make this difference because nothing can get out of a black hole, it is a particle that is causing the black hole to lose mass. So black holes have stuff falling in them, they get bigger, and they also very much slowly lose mass because of evaporating particles. Although this is hypothetical, we've never actually measured Hawking radiation. But we do think, and we're pretty sure, we know that matter falling into a black hole will make a black hole grow. So it gets more massive, and therefore its radius grows as well. But it's not at all a weird question to ask. It makes a lot of sense. Like, what is the shape of a black hole? What happens when stuff is falling into it? So that is the general idea here. Okay, let's see. There were more questions about this, and then I'll go back because there were 2 comments from Scott I wanted to answer. But staying with the black holes, do you think it would be possible for a neutrino to pass in and out of a black hole's event horizon since it is so weakly interacting? This is an excellent question. So neutrinos are a type of particle in the standard model of particle physics that are really, 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 really tiny. They're ridiculously small. But they do have some mass. They are not massless. We used to think neutrinos were massless, and then we saw that neutrinos actually have mass. So neutrinos are these tiny, tiny, tiny particles. There are 3 types of them. There's a electron neutrino, the muon neutrino, and the tau neutrino. And neutrinos have the cool things that they can change between these 3. They're the only particle we know of that can do this. Because they have a very small mass, it means they can't travel at the speed of light. Nothing that has mass can travel at the speed of light, only close to it. So neutrinos travel almost at the speed of light, but not quite. Now, even though neutrinos don't interact electromagnetically, they don't interact with the strong force, they do interact via the weak force, the weak nuclear force, and they also do interact via gravity. And this is the important thing here. They interact via the gravitational force, which means they're subject to the rules of gravity. If a neutrino falls into a black hole, it would not be able to escape. In order to escape a black hole, you would need to be traveling faster than light in a vacuum. As far as we know, nothing in the universe can travel faster than light in a vacuum, and we know for sure that neutrinos travel slower than the speed of light. So if a neutrino falls into a black hole, it will not be able to escape. Now, some of you might be wondering at this point, but neutrinos have mass, therefore, of course, they feel the gravitational force, but photons, particles of light, do not have mass. So how do they feel gravity if they don't have mass? Because if you think of Newtonian gravity, we're told that the gravitational force is proportional to the mass of the 2 objects involved. The bigger the objects, the more gravitational force between them. So photons don't have mass, so how do they feel gravity? Now here's the thing, photons travel through space-time, and gravity is just the curvature of space-time that is caused by objects with mass. So if you have a big object like a planet or a black hole or a star, this is going to distort space-time. It's going to create a dent in space-time. And then when photons, particles of light, are traveling through the universe, they're going to feel this curvature, this bending of space-time that is caused by the gravitational object, and they will experience this bending, this different trajectory. So even though photons don't have mass, they also feel the effects of the gravitational force. Neutrinos have very, very small mass, so they feel the effects of the gravitational force, partly because they have mass, but mainly because they are traveling through space-time. The mass of an object basically determines its drag effect through space-time itself. But anything in the universe is subject to the gravitational force. So neutrinos, even though they don't really interact much, they only interact weakly, they still feel the gravitational force. They would also not be able to escape a black hole. But it is an excellent question. Now I want to go back to the 2 comments that I saw there. Comment from Scott. I just somehow managed to randomly bite myself. So that's always fun when you just bite your tongue when talking. Comment from Scott, maybe that's what I'm thinking, that there are hypothetical planets sharing Earth's orbit, but on the other side of the sun. Right, you asked about Venus being called Vulcan. I am not sure if Venus was called Vulcan. There was at some point a hypothetical planet that might have wiped out the solar system. There's a conspiracy theory that is called Nibiru, I think, something along those lines. It's purely a conspiracy theory. There's absolutely not a planet hidden just the other side of the Earth. sharing our orbit the other side of the sun. It's absolutely not a possibility. But I seem to remember there was a planet that we called Vulcan at some point, but I'm not sure which one it was. So your friend wanted to ask about the potential for life on other planets. That is a great question. Life on other planets. Let me just see the black hole thing. I'm making a comment of life on other planets because that's a long answer. Okay, so I should remember to drink because I haven't drank yet and 20 minutes in. So do more massive black holes have higher escape velocity, or does it cap off at light speed? Very good question. It caps off basically. So the way you construct the event horizon of a black hole is you ask at which point do you reach the point, at which point can you no longer escape if you're traveling at the speed of light. So the escape velocity. Wait, let me think about that because I was about to answer something that I just need to rethink because I was about to just say so. The escape velocity should cap out at the speed of light. And before answering why, I need to recheck something because I'm currently thinking of the formula here. So, Vulcan was a hypothetical planet inside Mercury's orbit. Okay, so hypothetical planet inside Mercury's orbit that we did not actually find. Okay, perfect. So let me just check one thing here. Yes. Okay, so the escape velocity of an object, of a planet, of any. So the escape velocity is the velocity at which you need to travel in order to escape the gravitational pull of a planet or an object. So if you're on the surface of the moon has an escape velocity, which is the velocity, the speed at which you need to be launched away from the moon in order to escape its gravitational pull. Earth also has an escape velocity. Now, the thing about the escape velocity, which I had in mind and just wanted to double check before saying something stupid, is it is proportional to the mass and the radius, but directly proportional to the mass, to the square root of the mass over the square root of the radius. Because in black holes, the mass and the radius are directly related, it means that as you increase one, the other increases. So it doesn't actually change the overall escape velocity because they're increasing in the same way. And therefore, at the end of the day, the escape velocity is just going to be equal to the speed of light. Right. Just had to check it there. But by definition, at the event horizon of a black hole, the escape velocity is always going to be the speed of light. You can plug in the formulas and see that it has to be. Now, what happens when you get inside a black hole? Does the escape velocity go up? Well, at that point, it becomes a bit harder to define because the escape velocity is always defined as being on the surface of an object. Because once you go beyond the surface, if you go like to the center of the Earth, then the escape velocity is not just about the mass of the Earth, it's about how far into the Earth are you. So then you have the radius of the Earth at play and your distance from the center of the planet, because these are no longer the same quantity. So the escape velocity is always defined as being on the surface. Therefore, yeah, so it's always defined as being on the surface. So if you go inside a black hole, apart from the fact that we don't know what's happening in there, it becomes very hard to define escape velocity. Escape velocity is the velocity you need to be launched from the surface of an object in order to escape its gravitational pull. By construction, the event horizon, the escape velocity at an event horizon will always be equal to the speed of light. But square cube rule does not actually apply when you calculate the escape velocity. It actually crosses off. So this idea that, the gravitational force, the further away, if you double your distance, if you multiply your distance times 10, you divide the gravitational force by a factor 100. It has this inverse square law, sorry. However, when you're calculating the escape velocity, you end up with two squares because the velocity, when you compare the energies, it goes away. So the escape velocity is proportional to the mass over the radius inside the square root. And the Schwarzschild, the event horizon of a black hole, is proportional to the mass over the radius. Sorry, proportional to the mass. So then you can put them together. Let me just recap here because I just got lost there. Yes, usually the gravitational force does decrease with an inverse square law. So if you multiply your distance by a factor 10, the gravitational force goes down by a factor 100. When you calculate the escape velocity, this is not the case because you're putting together different equations. So it's a different equation that we're considering here. So no need to apologize to me here who got lost. The escape velocity is the velocity at which you need to be launched from the surface of an object in order to escape its gravitational pull. This is defined at the surface. In the case of a black hole, surface is kind of a weird term, so we take the event horizon. At the event horizon, the escape velocity is the speed of light by construction. Beyond the event horizon, we have no idea. It gets quite complicated at that point. So I hope that clears it up. No need to apologize for me who got lost there trying to do math in my brain. Always a bit different. The singularity is more or less a point, so you could call that the surface. Could you, though? Could you? It becomes very ambiguous to define the surface of a black hole, because that would imply that there's like a physical object there that one could stand on. It's also the problem, like how do you define the surface of the sun when it's a gas plasma? It's like where does one thing stop and the other begin? So defining surfaces is always hard. On rocky planets, it's easy. On icy planets, it's easy. On gas planets, you kind of say, okay, well, we contain all of the matter in a specific region. Now, can we really call a singularity, which is an object that doesn't make any mathematical sense, can we define a singularity as a surface? Singularity is kind of like the point where your equations break down. It's a point. Does a point have a surface? It gets complicated trying to define the surface. And then again, you have the mass everywhere around you, right? So it gets quite hard. So when we're talking about the escape velocity of a black hole, we take the event horizon to be the surface, even though it's not technically the surface. Okay, going back, because I missed a couple of questions here, and I do have the comment written down about life on other planets. I have not forgotten that. Just want to make sure I got all of the comments here. I know this was stated in earlier shows, but would a gravitational wave escape a black hole horizon? Love that question. Let me just catch up on the other comment here. The singularity is, yes, we went through that one. Okay. Could a gravitational wave escape a black hole event horizon? Love this question. Gravitational waves, ripples in the fabric of space-time. These travel throughout the universe. Now, the thing about gravitational waves is they are within the universe. Now, within Einstein's general relativity, within the theory of gravity that we currently have as the dominant theory of gravity, the one most people accept, gravitational waves should travel at the speed of light. And this might seem a bit weird, like why does everything travel at the speed of light? And light is just the most common example of this. It's actually the speed of information, the speed at which the universe can talk to itself, so to speak. Within Einstein's general relativity, there was a prediction that gravitational waves should travel at the speed of light. In non-general relativity models of gravity, known as modified gravity, this is not necessarily true, and gravitational waves could travel faster or slower than the speed of light. A couple of years ago, we got the first observation not only of gravitational waves, but of two neutron stars smashing together. So not black holes this time, but neutron stars. Two neutron stars smashed together, they produced a huge amount of gravitational waves. But also, they produced a huge amount of electromagnetic radiation. When black holes smash together, all you get from them is gravitational waves and some type of remnant, another black hole left behind. When neutron stars, so neutron stars are stars that have collapsed, but they weren't quite massive enough to be a black hole, so it's almost a black hole, but not quite. And it's a region that is so dense that protons and electrons can fuse together to form neutrons. So you have a star made entirely of neutrons. When two neutron stars smash together, you get an accompanying burst of electromagnetic radiation. A couple years ago, 2017, which is more than a couple of years ago by now, wow, time is passing quickly. At some point, LIGO and Virgo, the gravitational wave detectors we have here on Earth, were able to measure a gravitational wave signal coming from two neutron stars smashing together. And at the same time, the Fermi-LAT telescope up in space detected a huge gamma ray burst. This immediately triggered a signal to all the different telescopes on the planet, like go point in that direction in the sky. And people were able to see the shock wave of the two neutron stars smashing together, which is highly energetic plasma. And they were able to see this at very different frequencies. First, the gamma ray burst, and then gradually this moving right the way down to the X-ray radiation. So these neutron stars smashing together triggered Fermi-LAT, like, hey, look up there. Everyone looks up there. Then LIGO and Virgo check their detectors, like, hey, we found it too. This meant that for the first time we had multi-messenger information. So multi-messenger means multiple messengers coming from two neutron stars smashing together. We had electromagnetic part and we had the gravitational wave part. Here's a really cool thing. The gravitational waves and the gamma ray burst arrived on Earth within 2 seconds of each other. Given the ridiculously huge distance that these had to travel on their way towards us, the fact that they arrived within 2 seconds of each other means that they were traveling at the same speed up to 1 part in 15. Sorry, 1 part in 10 to the 15. So you have like 0. There are lots of zeros, count the 15 digit, and that's where the difference you'd find is in their speed. This means that gravitational waves and light rays, electromagnetic waves, are traveling at the same speed of light. This was awesome if you like general relativity, because this was a prediction in general relativity that gravitational waves should travel at the speed of light. And our observation showed that they do travel at the speed of light. And this is really cool. You consider the huge distance these things had to travel. The fact that by the time they got here, they were less than 2 seconds apart means they were traveling so close together in terms of their speed. So, if gravitational waves travel at the speed of light, they cannot escape a black hole. Gravitational waves follow the same rules as everything else. If they're traveling at the speed of light, they cannot escape a black hole. Of course, then you can have fun things that black holes themselves produce gravitational waves as they're moving through space-time, as they're colliding, as they're coming together, and those do then propagate outwards. But they're not really escaping from the inside of the black hole, but rather the black hole itself is producing these gravitational waves and sending them out. This is really cool. So it's a great question, but the answer is no, gravitational waves cannot escape beyond the event horizon of a black hole because they travel at the speed of light, and nothing can escape unless it travels faster than light in a vacuum. And yeah, these neutron stars that smashed together were 200 million light years away or so. 200 million light years away, which means 200 million years ago, two neutron stars smashed together. They sent out a huge burst of light, of matter, a shockwave, and gravitational waves, and we were able to measure it here down on Earth with a bunch of different telescopes and satellites, not just down on Earth, but around Earth. Thousands of astronomers across the globe came together and said, yes, we measured this in these different frequencies, we measured the gravitational waves, everything traveled at the same speed. And we learned so much from this event. Like this event, apart from producing a black hole remnant, also released three solar masses of gold. So 3 times the mass, 3 Earth masses of gold. So 3 huge chunks of like Earth-sized chunks of gold, like not actual chunks, but that much gold was created in this plasma. So it was a really cool event. We learned so much, and we've only found one case of 2 neutron stars smashing together so far. But there's a lot of hope that we will find a lot more of these. So the statement, nothing can escape a black hole, is really absolute. There must be an exception to every rule. That's actually not the case. There's this weird sentence of it's the exception that proves the rule. And that's actually, I believe, a mistranslation from the original sentence, because it makes no sense. An exception doesn't prove a rule. An exception disproves the rule. You know, a rule does not have exceptions. That is absolute. And the phrase, it's the exception that proves the rule, is actually, I believe, I might be misremembering, but I have in mind that it's a mistranslation from the original sentence. And then it just stuck, and people use it as like, it's the exception that proves the rule. And it actually doesn't make any sense when you think about it. Tangent aside, we have not been able to find anything that can escape the gravitational pull of a black hole. Once you're beyond the event horizon, it is a point of no return. Nothing comes back from that unless something travels faster than light in a vacuum. If we find something that travels faster than light in a vacuum, our physics is wrong, we chuck it out, we start again. Because this is an absolute, it's not an absolute truth, it's kind of like something that we very much expect to be the case based on everything we've ever observed. If you find something traveling faster than light, this means some of our equations are wrong. But very, very cool to think about something trying to escape a black hole. Maybe black holes are doing us a favor. Maybe they're keeping in the interdimensional creatures that are trying to attack our universe. Do not take this as scientists said interdimensional creatures are coming to us. Please don't take it as that. But someone could absolutely write a story about black holes actually being the guardians protecting our universe from interdimensional beings. I mean, it would be as far fetched as any other sci-fi show out there. So if somebody wants to write that, please go ahead. Okay, black holes. I'll give you a sec to process black holes. Ask me any more questions about black holes, and if not, I'll answer the question about life on other planets. And take advantage of tea being at optimal drinking temperature. Okay, I don't see any more black hole questions coming in, so we're going to talk about the possibility of life on other planets. Now that I finished tea. Tea waits for 35 minutes and then gets drank within 2 minutes. Right. Could there be life on other planets? This is a big question. We have not found any life on other planets just yet. And then it very much depends, what type of life are you asking us to find? Would you be satisfied with microscopic bacteria or microbes, single cell organisms? Would you be satisfied with a virus when we're not sure if viruses are technically alive or not? Ambiguous. So we have not found life elsewhere in the universe yet, but we've basically only looked on our own doorstep. Let's play a game of statistics. We are one planet out of 8 planets orbiting our sun. Our sun is one star out of billions upon billions upon billions of stars within our galaxy. Our galaxy is one galaxy in billions and billions and billions of galaxies out there, which means statistically speaking, there has to be another planet out there with life. Just a matter of statistics. So what is the probability of life on our planet? Now that depends. I mean, you can start from the fact that there is life on our planet. So that's already a question that we know. It's 100%. There is life here. What is the probability of this happening if you rewind? It becomes very hard to calculate. So statistically speaking, I am sure there is life out there in the universe, and we've barely looked within our solar system. Now, then we come back to the idea of what do we mean by life? Are we hoping to find intelligent life? Because that becomes a lot harder, because not only do you need the necessary conditions for life to emerge, you need the necessary conditions to keep this life-bearing, this habitability, this life-bearing status for a long time. Civilizations progress also at different speeds, and there's also a lot of different aspects to consider here. So I don't expect there will be many advanced civilizations knocking on our door anytime soon. Statistically, I think it's quite possible that somewhere out there in the universe there are other intelligent species. But we haven't found any yet. But there is a chance that there could even be stuff like this on one of the moons of Saturn. So one of the moons of Saturn, Europa, has an icy surface. Beneath the ice, there's liquid ocean that is heated by the geothermal activity of the planet. So it is the perfect breeding ground. It is the perfect environment to find microscopic single-cell organisms. We haven't found them yet, but we haven't sent a probe to go there and study them. Then, of course, we'd have to be very careful, because if there is something there, anything we would bring over in our probes could be damaging. So there is a possibility of finding the building blocks of life in different parts of the solar system and further out there in the planet, in the galaxy, and beyond the galaxy. So there is a lot of possibility for places where you can find life. And then we have to ask a question of, would life look the same as us? Now, I don't mean are they going to end up as bipedals, because that's, a series of freaks of evolution, happy accidents, and weird stuff that's happened that's led us to be the way we are. So I don't expect little green men that look like us, except they're green, or the standard, like Area 51 aliens. But a bigger question we have to ask, not so much how these species would have evolved, but the building blocks that make up these species. So we are carbon-based life forms. The main atom in most of our bodies is carbon. We are mostly carbon. Now, the question here is, could you have something that is not carbon based? Could you have life forms that don't rely on carbon? Now, here we rely on carbon, and it is the most abundant element we have around us, so there's quite clearly a connection here. Could you have another building block replacing carbon? And one very clear example of this would be silicon, because it has the right structure, the right chemical structure to also form building blocks in a nice way. This has been explored in some sci-fi shows. The Horta in Star Trek is a famous example here. But it's something really interesting to consider. When we're looking for life, are we limiting ourselves to our description of life of carbon-based life forms, or do we expand it to allow other types of life forms? And then also, what are the kind of markers that we're looking for? So life on Earth can't exist without water. Everything that we know of is water-based. But we've also found some organisms that don't need water and instead use arsenic, which would be poisonous to most life forms. So if we're looking for water as a telltale sign of life, are we potentially missing stuff that managed to evolve in environments without water? So it becomes a very complex question of, are we censoring our questions about life in the universe around our own preconceptions of what life should look like, and how do we not do this? Because we need to start somewhere. So we start with what we know, right? We start for something that is recognizable as life as we would know it. But if you allow for non-Earth-like life forms, then there's even more possibilities of spaces where there could be life. So the question was kind of vague of the possibility of life on other planets. There's a lot of ways life could evolve elsewhere, but you also need the right conditions and for long enough for this to actually develop into a species if you want a kind of an intelligent type of, or any type of civilization. Another thing that the universe, we are lucky in the fact that there's not a supernova close by that could wipe out our planet with a huge solar flare or a huge flare. If you're in a place that is quite close to potential supernovae, then it becomes quite hard for life to evolve long enough. It could be there for a short period of time and then stop being there. So there's a lot of layers to this. We want to find life, but that is also alive in the same time of the universe than we are. Yeah, life doesn't last for too long either. I mean, it has on our planet. We've been around quite a few billion years if you count all of the creatures here. So there's a lot of layers of difficulty here. Like, could there have been civilizations in the past that have died out? Could there be civilizations that are so far away that they're completely out of reach to us? Could there be civilizations much more advanced than us and see us as like these little unevolved creatures? The answer to all of these is maybe. We haven't found anything yet, but again, we've only really looked in our backyard. And it's very interesting. I think the universe would be a very lonely place if we're the only planet with life. Now, of course, the universe doesn't care what we think. I think it's quite likely that there are other life forms out there somewhere in the universe, but this is my own opinion. There is no evidence to say we have found anything. It's just, we're looking. We've seen a lot of places where there could be. We haven't yet found anything concrete. I think missions in the future to Europa and Enceladus, different moons in... Did I say Europa was a moon of Saturn before? I did, didn't I? Yeah. Anyway, Europa and Enceladus, these are cool moons within the solar system that could be harboring the building blocks for life. So there's a lot of things, a lot of places where we could find life, and especially if we then relax our definition of what it means to find life in the universe, I think we will find stuff. I'm hopeful that we will find within my lifetime. Yes, Europa and Enceladus. Yes, I'm hopeful that within my lifetime we will find some type of life form, single cell organisms on different planets or different moons within our solar system. I don't think we're going to find an intelligent, advanced civilization within my lifetime. I would be very happy to be proven wrong here. And again, this is just based on my own opinions. This is not something that I can back up just based on the way things are going and the chances of this happening. I think within the next 50 years, we will find microscopic organisms somewhere within the solar system, but we will not find an intelligent species just yet. Very happy to be proven wrong in the direction of finding more things. I hope that we found something within 50 years. It would be fun. Then you had another question here, Scott, of about holograms being sent to space, and I'm not sure what you really mean here about holograms. Now, a hologram in the sense of the way we usually see it is a three-dimensional projection of a two-dimensional object. So you kind of have these holograms where you have a screen and you project a three-dimensional object. Or you take a postcard that has a two-dimensional postcard image printed on it, and depending how you look, you see this 3D object. This has existed in various forms throughout history. We have the stereogram things that look like a basic image, and then if you focus your eyes kind of at a specific point, you see a 3D image pop up. That is a basic realization of a hologram. So what type of holograms you want to send to space? Why? What are we hoping to achieve here? Of course, we're not yet at the stage where we have a full-on holodeck a la Star Trek yet, but maybe someday we will, and that would be really cool. So what purpose would there be to send a hologram to space? What type of holograms you want to send? It's a question. It's like why would you do that? What do you hope to achieve? And what. Yeah, if you have a more specific question there about sending holograms to space, we can revisit this. But I don't see why there would be much of a reason to just send a hologram to space. Other than sending stuff to space is fun. So the second one, I'm no longer sure what the second one was. NASA is sending them. Could be. I'm currently not really sure why or what type of hologram people would be sending. Now, what could be the case is that people are sending records within the spacecraft, so that if some other species ever finds our spacecraft, they have a kind of record of humanity, like we did with Voyager 1, one of the Voyagers. So I'm not completely sure what NASA is doing, perhaps to reach out as a signal. It would be overly it wouldn't be an energy efficient way of doing it, because if you want to send a signal, you send a radio wave or an electromagnetic wave of a different frequency. But actually constructing this into a hologram is not so simple. So if you're going to do the extra steps of making this a hologram, the question is why? Are we assuming that like if you're doing it to communicate, are you assuming that whatever species you're encountering is going to know how to reproduce our hologram and what it means and how to interact with it? Kind of like you need a nice R2D2 where you just press a button and it spits out the hologram of Leia. That would be cool. Not quite there yet either. The Doctor from Star Trek, Voyager, or Rimmer from Red Dwarf? Oh, I'm going to go with both. To be fair, that's my default answer. If you ask me an A or B question, the answer is always both. So why pitch people against each other? They're both good characters. So let's just go with both. That's my default answer. Like when someone says cats or dogs, like, yes, I'll take both, thank you. I'll take one of each, 10 of each. This is just, you can't ask me an A or B question. I will always answer both. Okay, so I do actually have two questions written down, not from today, but from other weeks, that I promised to answer, and I've given a hand-wavy answer in the past. So they're actually even written in the caption of the video today, because I very much intended on answering them. So we've had the question the last 2 weeks about, can black holes have charge? The 2 weeks ago, I didn't know how to answer. Last week, I'd forgotten to check it out, so I hadn't answered. So NASA beamed a holographic doctor to the ISS about a year ago. Okay, right. So that's yeah, that makes a bit more sense now. So International Space Station currently has humans on it. I think Rimmer would ruin it somehow if we sent him. Yeah, maybe. So the International Space Station has a bunch of humans up there doing a lot of experiments. Now, of course, if something happens, like someone breaks a leg, now all of the astronauts do have some medical training, they have to, but ideally, sometimes you do want a doctor to visit, and you can't really send a doctor up to space, it's a bit hard. So then you can actually use holographic technology to kind of project the doctor into the International Space Station. We're not yet at the stage where the doctor can walk around and see the space station. It's not a fully fledged hologram. But in that sense, you can kind of send the image of the doctor to help out with the diagnosis. So then beaming a holographic image to the International Space Station makes sense, because you're sending it to other humans who know how to interact with this. Just beaming it randomly out into space would be a bit weird. But yeah, sending it to humans that we already know are out there does make sense. Charge of black holes. So black holes have three main properties. They have mass, which tells you how big it is. Mass is related to radius. They can potentially have spin, and they can potentially have charge. Now, this means obviously all black holes have to have mass, but then between charge and spin, or spin is just like magnetic moments, so if the black hole is spinning, and charge is very similar to how we know electrons are negatively charged, protons are positively charged. What about a black hole? So then you can have four possible configurations. You can have charge but no spin. You can have no spin but charge. You can have neither, or you can have both. Now, we know that most black holes should have spin. Statistically speaking, things in the universe like to spin. It's quite hard to find something that doesn't have spin. So most black holes do have spin. Adding charge in adds a whole new level of complication there. There are limits. We know that if a black hole... So when black holes are created, they are not created with charge. We have not yet found a mechanism to create a black hole with charge. Now, if objects fall into a black hole, this black hole can gain charge, and this would lead to a black hole having charge. But there is a limit. If you express the charge and the mass of the black hole in energies, they have to be equal. You can never have more energy units of charge than you do of mass. So black holes can have charge if they accrete a lot of stuff that has one charge. But what is more likely to happen is they accrete equal amounts of positive and negative charges, so black holes are neutral. Usually when studying black holes, we say spin equals 0, charge equals 0, because it's the easiest case. If we want to add one layer of complication, we add in the spin, because we know that black holes do actually have spin. Adding in the charge makes it even more complicated. So it's not something that we usually do. But black holes are a solution to Einstein's equations and of general relativity, and you can find at least four possible solutions for spin and charge, and the different combinations of spin charge, charge spin, neither, both. So black holes can theoretically have charge. We don't think black holes can be created with charge, but they could acquire charge. However, we usually consider that black holes are neutral. So that is a question that was lingering from 2 weeks ago and then was asked again last week, and I never got around to answering it. So I actually read up on that before doing the stream today. There was another question that was asked a couple of weeks ago that is a super fun question, really interesting question to think about. Which is the question of what would happen if our universe had two time dimensions. Our universe, to the best of our knowledge, has four dimensions. It has three space dimensions and one time dimension. So you can go up, down, left, right, in, out, three space dimensions. You have three axes along which you can move. And there's one time dimension. We move forward in time. You can't go back in time as far as we know. This one dimension of time can also be tied into things like entropy. So the amount of chaos you have in a system. The time dimension gives us the change between event A and event B. If I have my pretty tea mug here, this is event A. If I throw my tea mug on the floor and it's broken, that's event B. There is clearly a pre-state and an after state, but you don't expect the mug to spontaneously assemble again after it's been broken. This is entropy. It gives us an hour of time. And someone asked me what would happen if we had two dimensions of time. And the answer is we have no idea. So I answered this a couple of weeks ago on the stream and said we have no idea. And then I said I would discuss it with colleagues, and I did discuss it with colleagues one day. And the answer was no idea. We have no idea how we'd even build this. And then we got down the question of okay, are we sticking to four dimensions and replacing one of our space dimensions with time? Or are we adding a whole fifth dimension here? If you're adding a whole fifth dimension, you need to resolve the Einstein equations in 5 dimensions. If you're sticking to 4 dimensions, then we have the thing that we have kind of the metric that we call, which relates how all of these dimensions. And usually you take 3 of them to have one sign and one to have another. So if you take the 3 space ones to be positive, you take the time dimension to be negative. This is just a mathematical idea. Or you can take the other approach and define what space is being, time is being positive and have 3 negatives. This is a matter of preference. People have a lot of opinions on it. As long as people are consistent, I don't care which they use. Now, if you added a second time one, whatever you do, you'd end up with 2 positives and 2 negatives, which mathematically means you need to resolve everything. So I was asking my colleagues, what would the universe look like with 2 dimensions? And none of us were really sure how to even start this conversation because we don't have anything we can point to. Right? What would it mean to have two time dimensions? I mean, we don't even know what the force is, how anything would look like in the universe with two time dimensions. We wouldn't even be able to describe space time. We'd have to go back and start everything again. So, what would happen if we had two time dimensions? It would be a headache for a lot of physicists. That was our conclusion, that you'd have way too much math to solve. Now, of course, if we were in a universe with two time dimensions, we already would have solved everything, assuming this, so it wouldn't be new work. But if another time dimension suddenly appeared by some random mechanism which we don't think is possible, it would mess up everything in weird ways. We have no idea how we would even begin to describe a universe with two time dimensions. Like mathematically, we don't even know where to start. It's like you go back and start from scratch, you redo everything. Nothing of what we have is valid. Would the speed of light still be constant? I mean, speed is velocity, distance traveled over time. What happens when you have two time dimensions here? Then time becomes a vector instead of a scalar, which means it's an arrow instead of a point. It just becomes mathematically very difficult to know how to grasp this idea, and then even harder to try to physically explain what is happening. It will be wibbly wobbly, timey wimey, very confusing. If someone wants to write a sci-fi story about two time dimensions, then go ahead. Given that we don't know what would happen, you can have fun with it, come up with whatever you want. It's very difficult to know what actually would have happened and what might be happening in a two time dimensional universe. So yeah, it's definitely a fun question, and we all had fun thinking about it when I brought it up in Coffee Break. And the conclusion was kind of like, yeah, that's interesting thought experiment. Let's move on. So we don't think that a universe with two dimensions of time would help us much, or would be in any way something we could describe. So it's fun. It's a fun thing to think about. But yeah, we would need new math. We would need to start again. A lot of what we know would no longer apply. We'd have to resolve things. We'd have to add new elements. It's a whole new beast. It would be fun to play about with, but also we decided a headache and something that none of us actually want to deal with. So we're quite happy that we have three space dimensions, one time dimension, maybe some hidden dimensions that we haven't yet found, but we don't expect to find any more time dimensions lurking in the background. Three space dimensions, one time dimension. That should be enough for now. So, okay, we are almost at the 1 hour mark. So time to start wrapping up the stream, unless anyone has some last minute urgent questions to get in. So we've had some really cool topics today. I feel like we've been talking a lot about black holes the last few weeks, but there's so much to talk about with black holes. So it's always a fun topic to come back to. Always fun to come. The link for NASA holography story. Yeah, links don't show up here, at least not. Yeah, you can't post links in YouTube, which is partly good because of all the spam comments that people leave when the links get blocked. But if you want to send me a link, as always, you can ping me on Twitter. I do check my Twitter messages. Not often, but I do get push notifications, so that drags me back to Twitter. You can always reach me on Mastodon. So my Twitter handle is DCHooper91. My Mastodon handle is DCHooper91 at tech.lgbt. And the easiest way to reach me is email contact@cupofcosmology.com. You can always send me emails. Also, there's cupofcosmology@gmail.com. They both go to the same place. Currently, I don't have any guests scheduled in for Cup of Cosmology. This is rare. Part of the reason I don't have any guests scheduled in is because the next couple of, like April, I'm going to be traveling quite a lot. May, I'm going to be doing some trips as well. It's full-on conference season. So I'm not quite sure about which Sundays there will be streams, which then makes it harder to schedule in guests. Like, hey, I want you to come to my show, but not this Sunday, this Sunday, this Sunday, or this Sunday. So currently, there are no upcoming guests, but I do have a list of names to go back to when I do bring back guests. Next Sunday, there should be a stream as usual. So next Sunday, 26th, there should be usual Cup of Cosmology. And a reminder to everyone that in Europe, we change our clocks next Sunday. So that means those of you who already changed your clocks 2 weeks ago, I'll be back to my usual schedule next Sunday. If you're changing your clocks with me, the stream will be at 7 p.m. European time. That's when it always is. So whichever time zone you're in, make sure you remember that next week I change my clock, so then the stream is going to change by an hour. As always, there is a time zone converter on cosmology.com. As soon as the clocks change, it will be updated to have the new information as well. So then you can always find the right time in your own time zone. You can go to cosmology.com, click on, scroll down, and there's time zone converter right there. Should be online next Sunday, same time as today. I might actually do a special topic next week. I have some ideas, and if I have time during the week, there will be a special topic next week instead of generic questions, which is always fun as well, but just requires a bit more preparation. So I hope to see you all again next Sunday. As always, thank you everyone for the questions. It's been great fun. Feel free to reach out if you have more questions or comments or things you want to talk about. Always happy for anyone to reach out to me. Otherwise, I will be back online next Sunday. I hope to see you all next Sunday. And in the meantime, I hope you all stay safe and take care of each other.